Hello, this is the final presentation for debate distributed systems, and our final project is called Debatrium. Debatrium is a distributed multi-agent AI debate platform hosted on AWS that tackles a fundamental problem with how AI answers questions. You ask a single model something complex, and you get one perspective, one reasoning path, and one set of biases, with no mechanism for self-correction or peer review. Real intellectual processes don't work that way. Science has peer review, courtrooms have opposing counsel, and engineering has red teaming. Quality emerges from structured disagreements. Debatrium applies that same principle to AI at a cloud scale and fully automated. Debatrium works when a user submits a question and a system spins up 9 agents across 3 tiers. 3 research agents, which argue the positive, neutral, and negative cases in parallel. 3 critic agents, which evaluate all research findings across logical consistency, factual accuracy, and completeness. Finally, 3 judges that score the debate on fairness, accuracy, and consensus. If the average score falls below a 0.85, the judge's feedback is automatically injected into the next round's research prompts. The agents literally read what they got wrong and try again. Up to 3 rounds, every decision, score, and critique is returned to the user as a fully audit trail. The result is structured as a multi-perspective answer with explicit reasoning and convergence scores, substantially richer than anything a single model can produce. This matters because single modeled answers are increasingly being used to inform real decisions in research, business, education, and beyond. Debatrium is useful precisely in the case where being wrong can be costly. For example, nuanced policy questions, contested factual claims, or multi-sided ethical dilemmas. By forcing agents to challenge and refine each other's reasoning, the system catches blind spots that no individual model would flag, giving the user not just the answer, but confidence to trust that answer.
So regarding the architecture, any request from the user will be hitting our API gateway that we have pre-configured. And once the requests have got to the API gateway, we have a custom orchestrator, which is a Lambda function that automatically gets triggered, and it would dispatch the query that it receives from the API gateway to the research tasks SQS queue. It creates 3 copies, one for different angle, for positive angle, negative angle, and for the neutral angle of the same question. Once it hits, it dispatches the task to the research tasks queue. The research agents, the nodes, will compute the agents in the autoscaling will do the processing, and once they finish, they would put the message into the research results queue. And based on these results, based on each iteration, we will also have a custom Lambda function that checks and gatekeeps messages that are output to the results queue. And so once the all results have been piled up to the once they have reached the queue, the research aggregator Lambda function will actually store each entry in Redis. And within this Redis, it also maintains a counter value, which monitors if, for example, like for the same question, if 3 messages have arrived in the cache, then it would dispatch those tasks from the Redis queue, from the Redis database to the critic tasks queue right over here. And also, like, it has a dispatch log so that whenever like any 2 Lambda invocations trigger the same output, one Lambda function is going to set a custom dispatch log in the Redis so that the other Lambda function won't actually dispatch the same tasks to the critic tasks queue. So again, after the critics are on the SQS queue, it will be dispatched into the critic agents, basically, right? So each critic agent have a different lens, and based on that lens, they will compute their findings. And again, they for each message on the results queue, a custom critic aggregator, a custom lambda function is going to get triggered. This basically does the same thing. It stores each message in our Redis. It also gatekeeps, and like it has a counter value. So for each, it would wait for 3 results for a query until they arrive. And once the 3 of them have arrived, it would dispatch those tasks to the judge tasks queue. And again, after the judge's SQS queue is going to dispatch tasks to the judge agents. And once they finish their task and put the results to the queue, the aggregator will again do the same thing, but in this case, it checks the average score of the judges, right? If it's above 85%, then it's done, right? It goes straight to the results queue. But if not, it would dispatch those tasks again to the research tasks queue so then they can be re-evaluated, and the whole process continues until a max round of 3 is reached, or uh, the threshold of 85% is reached. So over here, you can see a bunch of instances running in different availability zones. So for example, for the research agent, one is in 1A and one is in 1B. All of these have been started from the auto-scaling group that we pre-configured. And so I'm just going to demonstrate how the debate flow is going to continue by simulating a real scenario and deleting a bunch of agents, right? This may happen in a real scenario, and so I'm just going to go ahead and stop these instances. So there's scheduled to stopping, so I'm just going to go ahead and ask a question. This is the question. I'm just going to go ahead and start the debate. So imagine there's only one node available for to process each task, right? Let's see what the queues are doing. You see, like the research task is actually being picked up by the queue and by the agents, and it's being processed. If I refresh again, you see the aggregator function does its thing and it pushes it to the critical task queue. Again, this process continues. So at each step, we can also check the Redis state. We can check it by, you can see these are like the first results based on the hash value, but over here you can see, for example, like what I can do is scan 80 again, and for example, like we can see the results of so they reached round 3. So I think yes, they're on round 3. And then we can see here, for example, if the debate is already here. Oh, I didn't copy it correctly. So here you see all the results, all angles for the third round of the debate have already arrived in Redis, right? So it also keeps track of each count. It gatekeeps, and also it checks. It continuously monitors this. Imagine like I'm running only one instance for each agent at the moment. Let's go to the debate. So I think it's being judged. Oh, so it's finished over here. So over here, you can see like it went on for 3 rounds. The average score of the judge is around 70%. It say that the neutral angle for the question is basically the winner, right? We can also go about to the S3 or S3 bucket. We can check the results. Can you stop it, Michael? So once the results are finished in our S3 bucket, in our debates, our specific debate has the ID of this. And so it's this one right here, the final results. If I open this in new tab, this is the actual JSON that's actually being placed in our S3 bucket. We use this for long-term storage. Yeah, and at each step, we have logs for each component For example, like we can check if the judge aggregator is doing this thing. So if there are any issues, we can go here and diagnose them easily. Everything has logs, and so over here you can see that the results are being written to this S3 bucket. It's being sent to Redis, right? We can also see the average score over here. So if there are any issues, you just go to the logs and review the logs. Each agent has its own log, so it's easy for diagnosing basically. Even all the lambdas have our logs, so you can just go ahead and review what's happening at each step, right? And also like on the UI, we can show this is like the neutralize the winning angle, but like for further analysis, we can just go down and we can see the independent score of each judges using different lenses, right? Our judges will be using these three different lenses when judging the content of the researchers and the critics. And so we can see a um, detailed view of the debate and the scores of each angles. And can you stop, Michael?
So speaking about the distributed system properties, we decided to focus on four of them. The first one is the fault tolerance. And speaking about it more, first we have a heartbeat thread. Basically, the idea is that each agent sends kind of heartbeat signal. And when it's kind of down, we know that the agent is kind of down. And the content, the message itself that is processing is not lost. The SQS visibility is going to be restored, so the other agent can process it. And the next one would be poison messaging. Basically, like our message gets corrupted or poisoned, and this kind of stuff is handled on the code level of the agent. The same with the Redis failure, which is also kind of considered on the code level of the agent. The next part would be consistency, and since to make sure that it's going to be consistent, because there are going to be many Lambda functions running at the same time, we decide to use a Redis atomic operations with an X dispatch log. And moreover, to avoid having the same content multiple times in our SQSs, we have a content-based deduplication. Now, speaking about the scalability, we decide to use auto-scaling groups. And since other stuff like uses Lambda functions, which is also scales pretty nicely since it's a serverless solution. And for the SQS, it also scales nicely since provided by Amazon, and Amazon is very like nice about that part. It scales really beautifully. Now, finally, speaking about the last part, which is availability, we have our solution running in two availability zones. And moreover, as an insurance, we have our elastic cache running on the second availability zone. So basically, we have a one primary elastic cache and one replica elastic cache.
We have come up with a proper testing mode where we've tested all these distributed system concepts in our debate system. The first thing is agent crashing mid-processing. Like Manzoor already said, when the heartbeat stops, there are the SQS messages visibility expires. So we make sure that the visibility comes back and then another worker picks it up. So this ensures that the debate completes no matter what you do. We've also created a Redis network partition. If there is a problem with the Lambda functions accessing the Redis port, orchestrator will fail fast with an HTTP 503 error so that it safely exits. There is also partial agent failure, which we've demonstrated in the final demo, where uh, only one of the two research agents is active. Debates still complete, but they are just more serial and parallel debating does not take place. Another consistency measure was poison message injection. If our handler already drops the malform payloads instead of making this affect the debate system. We also have message deduplication. If the ID is same, the SQS returns the same message ID and does not reprocess it. We have concurrent debates run to check the scalability, and we've launch 3 or 4 debates simultaneously, Redis isolates these properly with debate ID. And if there is any S3 write failure, the bucket policy is stripped, and then the judge aggregator will fail gracefully. All these tests have been run, and the test results are included in our repo.
So during this whole project, we had many challenges. The biggest one would be our design-related challenges, because this was kind of our first experience designing this kind of large-scale solution. So first, we had many issues that we discussed with the professors, that he mentioned that our problem was in our design, like single point of failure, that our scaling wasn't that good, like it was more vertical, but we wanted to do more horizontal. And another thing is that we wanted to make our solution as much as fault tolerant as possible. So we wanted to make it stateless, so that even when something dies, it's easy to fix and something like that. And then that kind of stateless approach required us to change a lot of our design, like how the aggregation will be done and everything. Another problem was that in our original design, we haven't thought about the utilization, like how much tokens would be consumed. And the problem would be like context explosion, meaning that the longer debate goes, the bigger context gets. And to fix it, we had to introduce a summary after discussing with professor, and many more challenges related to design, which were resolved with the help of the professor and discussing them. Another failures would be related to the AWS environment itself. First, failures like challenges. The first one would be the learning curve. Like the second one would be more related to the scope what the AWS provides, because it's still not like full available AWS. It's kind of limited, so we had a lot of limitation, like on the IAM roles and everything. We couldn't make lots of EC2 instances and other kind of resources. A lot of limitations. Another thing was that because that environment wasn't kind of actually made for this kind of development, there was a lot of failures related to the infrastructure buildup, meaning that since we want to make our project as much reproducible as possible, we made like automated scripts. But because that kind of stuff wasn't created for this kind of purposes, we had a lot of failures, especially related to resetting and stopping the environment. Other failure challenges would be related to the OpenAI API key itself, because we had other kind of issues related to the amount of money that we put in there, and at some point it wasn't enough. So we had to add more money, and there was like other kind of challenges, meaning that we didn't consider the amount of resources that it would take. And the list could be going on, but these were the more important challenges. Now coming about the OpenAI related failures, the first failure will be related to rate limitations. So we had many issues because of that. And the second thing would be kind of related to infrastructure a little bit, because every time we reset and stop the environment, like kind of testing again, there would be problems that the older tokens would be cached. And then we had this kind of failures that we have to manually delete something and then update the token by ourselves. So now speaking about the points of improvement, I guess we could start first about the thing is that right now there is no way to know the like proper ordering of the events. And to solve this problem, maybe in the future we would like to introduce lamp vector clocks, so that at least we could somehow at least get some kind of sequential ordering. The second problem would be related to the consensus threshold. Right now, it's simply hard-coded, but in the real life, it's not a good idea to simply hard-code this kind of important factor. And we could apply more consensus mechanism algorithms. Another problem would be related to there could be some theoretically there could be inconsistency state. Is when at the end when the debate finishes, it's kind of saved to the Redis, but it's not saved. Like there could be failure saving to the S3 bucket, and this kind of inconsistency could be occurring, for example. And to solve this kind of failure, we would also use more like consistency algorithms that we got during the lectures. Now, speaking about the other point of improvement would be the AWS environment itself. Due to a lot of limitations, our hands were literally tied. We could improve the security at least way better with having more IAM roles, having better EC2 instances, and other kind of resource-related problems.
Hi, I'm Alekia. I'm currently pursuing my master's in computer science at George Washington University. I will be graduating in May 2027. Prior to this, I was working at Dell for 3 years, and I have experience with Microsoft Azure and building highly scalable throughput microservices and REST APIs.
Hi, my name is Mansoor, and I'm a graduate student at the George Washington University. I'm doing my master's in computer science, and I'm expected to graduate in May 2027. I'm an ICPC World finalist and IOI medalist. I'm very passionate about competitive programming, large-scale systems, distributed systems, and everything system-related.
Hi, my name is Yuel Kubert. I'm a graduate student at the George Washington University studying computer science for my master's. I've been working on deep learning recommendation systems as a researcher at the University of Michigan, and also like I've been building private cloud infrastructures using OpenStack for enterprise applications. I'm really interested in distributed systems, networks, and how they can be employed and used in real scenarios.
All right, my name is Michael Womack. I am a student here at GW. I will be graduating this December, and I'm currently an embedded systems software engineer with 3.5 years of experience.